Welcome to our first lecture. In this lecture here, we're just going to spend some time talking about reverse engineering and what it is, and really talk about or hit on some of the high points for the course and some of the goals that we'll have for the semester. So we'll start off with the definition of reverse engineering. And so you can see here a rather lengthy snippet that I pulled from Wikipedia. Really what it's getting down to is, what is it? Well, it's really the process of taking something that we don't understand necessarily how it works, and taking it apart until we understand how it works. In the sense of software, which is what we're going to be looking at for the course, what we're really focusing on is looking at software in which we don't have the original source from, or we don't have the blueprints, how a protocol, maybe if we look at networking, how a protocol actually operates, and understanding how that works. The course is really going to be broken down into two primary components, in which I think you'll find that everything really builds upon itself, that a lot of the topics that we cover in the first half of the course are going to continue to build all the way to the very end of the course. And that first half, you're going to see that we look at static and dynamic analysis. And with static analysis, what that generally means is that we're not running the program. We're not executing the software or the binary in order to understand how it operates. When it comes to dynamic analysis, then we are. We're going to use execution of a program in order to further understand how it works. So generally speaking, we're going to have about the first half or so, maybe a little bit more of the course, but we'll be spending a great deal of time working on and working with static analysis and using the tools that will aid in our understanding or our skill set for that static analysis. Then when we move into more of the second half, we'll be doing more dynamic analysis, and we'll also be looking at a little bit of exploitation at the end, although this isn't necessarily an exploitation course. But it is important to understand some of those security flaws that are introduced into programs, how we can exploit those, as well as some of the defenses that have been put into place to help mitigate those. As we move into that dynamic analysis, then we're going to be using things like a debugger much more in order to help us understand how a program is executing, in order to understand how it's executing in real time by executing the program. What you'll find then is in both, that the core of both techniques is an understanding of assembly. And we're going to be looking at disassembling programs in order to inspect those instructions, in order to understand how that program is executing. This also, just to deviate a little bit, gives us an opportunity to think about and discuss cyber operations, because a lot of you that are in this course are a part of either the undergraduate cyber operations or potentially the graduate doctoral level. And what cyber operations is, because it's a little hard sometimes to precisely nail down what is it. What does a career look like? What does a job look like with a cyber operations degree? And this really, I think, helps to highlight what it is. Cyber operations is designed, especially if you look at the doctoral level program here, the doctorate in cybersecurity. It's looking at being able to reverse engineer in order to understand some of these protocols, how we can reverse engineer a binary in order to really understand how it works, and then being able to find flaws, find vulnerabilities, exploit that perhaps. That's a lot of what it is. So if you haven't taken some time, especially if you're at the undergraduate level, in thinking about what is a cyber ops, what are you going to do with cyber ops, think about that through the course. And certainly if you have questions or run into any potential internships or have any insight, share it with us. Put it in our Slack channel. Send me an email. I can share it with the class, however you feel comfortable doing. So, as I mentioned, a lot of the course is going to kind of revolve around disassembly. That is, we're going to be working with the machine code, the binary instructions, the binary of a program, and we're going to then use something called IDA Pro, in order to create assembly instructions from that resulting binary, from that machine code. We're going to be inspecting that in order to figure out how that program works. And we're going to be doing that statically through a tool called IDA Pro, and then dynamically through things like WinDebug or potentially Immunity. So when we look at languages, we generally have these generations or levels. Oftentimes you hear people say that we program at higher and lower levels. And it's all generally true. right? We normally think of binary as the lowest level. I mean, that is the machine code. And we could certainly program at that level if you wanted to, although it would be very painstakingly difficult and time consuming because you'd be writing in machine code. That next level is assembly, and that's where we'll generally spend most of our time in the course, is working at that assembly level. Higher than that, we have Fortran C, and then above that, we go into languages like C++, Java, and C#. And we'll talk about here a little bit today, and then throughout the remainder of the semester, the process of compiling, of assembling, of linking, of executing, of how the Windows or whatever operating system you happen to be using loads a program into memory for execution. We're going to be spending most of our time working with a Windows environment. The lab that we have set up for in the IA lab is Windows, and we're going to be working with, for the most part, again, 32-bit assembly, 32-bit programs. And so we'll generally stay in the Windows world and in the 32-bit realm as well. Point out some 64-bit when it's appropriate, but what you'll find is that there isn't a tremendous leap from 32-bit to 64-bit. And so there are a variety of reasons why we're staying at 32-bit. One of which, probably the primary of which, is that a lot of skills that you'll use for reverse engineering, revolve around that malware analysis, and a lot of malware is still written in 32-bit, not a lot of it's 64. So that's one of the main reasons. But regardless, I don't think you find it very difficult once you get these skills down in the 32-bit world to make that jump to 64-bit, or maybe pick up a different architecture like ARM or something. So why is this difficult? Why is this hard? And what you can see here is a screenshot out of IDA Pro. And what we're looking at is a couple of different views. The one on the left is just kind of the overview, that is showing us kind of the big picture function that I was looking at the time of the screen capture. And what you see on the right then is what's called graph view. And what graph view does in IDA Pro is it just shows us blocks of code that are somehow related. You can see here that there are two blocks visible in this particular screenshot, and that there is a couple of arrows. One arrow loops back around, another arrow goes from the top block to the bottom block, and then that third arrow, the one on the right that's green, comes from somewhere up above and skips that middle block altogether. And that just shows us, or helps to show us, really how the code fits together, how the instructions in those blocks are related to other instructions in other blocks. And you'll have two different views, and we'll get into this as we get into IDA Pro, and that you'll have this flow view, and you'll also have a linear view. And it'll really be up to you to decide which view that you prefer. I generally work with this graph view. That's what I prefer, and that's where you'll see most of the time that I'm doing any screenshots or recording my desktop or anything. This is what I'll be using. But why is this hard? Well, what you're looking at then is a very small portion of a function. You can see that as indicated from that graph view on the left to what we're seeing on the right. And this is just a small function in a much bigger program. And so it can take quite a bit of effort to look at and trace through every one of these instructions to understand exactly what it is it's doing. This right here just happens to be a domain name generation algorithm for a sample of CryptoLocker. So CryptoLocker is ransomware. CryptoLocker, CryptoWall, they've all kind of fall under the same family. It's malware, of course, and it's ransomware. It encrypts your files on your computer using encryption. It does it correctly, and the only way that you can get those files unlocked is to pay the bad guys for the keys, because it uses public-private key. So in the grand scheme of things, something like CryptoLocker, while this is an important component, its ability to connect back to a command and control server to get keys to encrypt your content, it's also a very small portion of what this program is doing. And so it becomes very difficult because you can spend a lot of time tracing through these instructions, trying to figure out what a program is doing. I want to encourage you at this point, especially as we start working our way into the labs, is that some of the labs we're going to spend a lot of time looking at every single instruction, and I'll intentionally keep them relatively short in order for us to do that. Some of them, though, you're going to be able to just focus on what's important, right? And that would be an example like this. Let's say that I was looking at CryptoLocker, and the only job I had for this particular binary that I was looking at was to figure out how it generated domain names, right? Then I would want to focus in on this And IDA Pro might not even be my best tool. I might have other tools that I could run that malware dynamically and just have it go ahead and generate them for me, right? It's completely up to you as the analyst, as a reverse engineer, to figure out which is the best approach. But anyways, so sometimes you can focus. You can try to pinpoint on what you're looking at and just focus on that and not get lost in everything that you're looking at in a program. And so don't always get bogged down with that. And I'll make sure that as we get into the labs, I kind of point that out, what I think is important and what's not. If you need to spend time going through all of the instructions and all the code blocks, or if you just need to focus on what's important. And of course, if you get lost, let me know. So we have the normal process of compiling and running a program. That is, that most programs that we program in, they're going to use a compiler, they're going to use an interpreter, they may use a preprocessor, they may use an assembler, but they're going to generate that machine code. Then a linker is going to come along, it's going to do some linking, we'll talk more about that a little bit later, and that will create an executable. That'll create something then that operating system can load into memory and begin executing instructions. The reverse of that is difficult. The compilation process is lossy. That means that with machine language, there are no variables, there are no functions. It's a series of addresses that contain either data or instructions. And so oftentimes the only way we can determine what type of data we're dealing with is in how that data is used. And so we lose some of that. We look at the source of a C program, we can see it's an integer variable, right? We look at that in assembly and we might not be able to tell. We'll have to read or trace through that program in order to determine exactly how it's being used. Compilation is many to many. That means that the source can be translated to assembly in many different ways and vice versa. It depends on the compiler. It depends on optimizations. We'll talk a little bit about optimizations and optimizing compilers throughout the course. And that can have a big impact on the resulting binary, the resulting machine code, and that the same source can produce different machine code, a different binary. The program might execute the same, but if you open those two different versions up in IDA, you might have two different databases or small changes in the two databases that you're looking at. It can also be dependent on the language, whether you're on Windows or Linux or Mac, whether you're using Delphi or C or Fortran or any variety of language out there. So there's a lot of variables that can make it very difficult. Again, we're going to focus on a Windows environment, and the programs that we'll be looking at will be predominantly 32-bit. And so adding that in as just a way to help make the course and kind of this transition into the world of reverse engineering just a little bit easier. So why do we do it? Well, as I mentioned, probably the first one is malware analysis, right? A lot of times with malware, you don't have the source unless law enforcement gets lucky and they catch they seize the assets of someone that's writing this, authoring this, but that's not usually the case. Oftentimes we're dealing with machines that are infected, not really sure how they got infected, and now the reverse engineer, the malware analyst, has the process or the task of going through and trying to figure out what exactly it is. What does it do? How does it infect? What are the artifacts that it leaves behind? How does it remain persistent? What is it doing? Is it exfiltrating data? If so, what type of data is it doing? How is it communicating over the network? A long list of things that has to be done, all because we don't have the source. We don't understand how that program is written and built, and so we have to go about it through reverse engineering. Another process, vulnerability analysis. And this is becoming very important, a very big component in the world of software, not just for ensuring the security of a program or checking for bugs, and not also for for malware analysis, but in just software that's been out there for decades even, that is now being really scrutinized, whether the source is available or not, and looking for vulnerabilities. A lot of the bug bounty programs that are out there, those are bug bounty programs that are encouraging researchers, security analysts, to go through, look at the code, whether they have source or not, try to find bugs, and then if they find bugs, report it to Microsoft or Google or whomever, and they receive a pretty good payday. And so there's a lot of good money in that as well. You might be doing it for a company, and that you're making sure or helping to ensure that the software that's being released is in fact secure, or as bug free as you can make it. And so vulnerability analysis becomes another big component of it. Software interoperability, and there's a handful of others that as you're going through the first reading, they just kind of highlight or touch upon. So I'll save the rest of those, or I'll leave the rest of those for the reading for you guys. So how does it work? Well, we have this, what your author in the IDA Pro book considers the basic disassembly algorithm. Step 1, step through, I think, step 4. We start off with looking for the code for well-known formats, right? So we're taking a tool like IDA Pro, and IDA Pro is, we're going to give it the task of taking this binary blob of data and turning it into our understanding and showing us the program, at least that assembly level machine instructions. So what it does is it looks for and tries to identify a well-known format, whether that's portable executable, ELF, the executable linking format, or the Mach OS 10, and a handful of others. Yeah, you're going to have limited ability to read these file formats because the free version of IDA is very limited. It's very restricted. If you purchase IDA Pro, you'll have more, more formats than just this available. These are important though, because not only is IDA going to try to parse these in order to understand where does the code begin, but that's what the Windows loader, what the operating system loader does, is it loads these files, it understands this format, so it knows where to start executing code. We're going to spend some time later on in the course. Our first project will be the portable executable. We'll go through and we'll get a pretty good understanding on how we parse it, how the Windows loader parses it, and how we can pull data out of that. So locate that initial entry point. That's really the point. We take that binary, the operating system loads it into memory, and then it knows where code is going to begin, where those instructions are going to begin that will be executed. Same thing for IDA. It needs to load it into memory, and that needs to start disassembling those instructions to show us here are the instructions for the program. Okay, from 2, it goes to the initial entry point, and then it starts disassembling. So that's taking the machine code, it figures out the mnemonic and the operands, and that's the basics that you learned in assembly, in 314 or wherever you took assembly. We have the mnemonic, we have the operands. What is the instruction, and what are the operands or the arguments for that instruction? In x86, again, this is largely what we'll be looking at for the course. They are variable length, and so it's a little bit more difficult in that IDA Pro has the task of figuring out what instructions are variable length, because if it messes up that length and it includes more of the opcode than it should, it can mess up the whole disassembly. And so that's one of the tasks that it has in order to ensure that it is in fact disassembling correctly. Okay, step 3 then is to display the code, and we'll be using the Intel syntax versus AT&T, so there are different syntaxes out there and available. If at any point in time the assembly looks different than what I'm seeing, or maybe you're reading something online and it looks different than what we've been using because the operands are in reverse order, then that's likely because it's an AT&T versus Intel. We'll be using Intel, and I believe IDA is set up that way by default, so it just works out well that way. So it's going to display the code, it's going to look up libraries, it's going to build references, we'll talk about cross-references, we'll talk about libraries as well. And what it's trying to do is just to make it easier to understand exactly what's going on in the program. If there's a call to printf, it's trying to identify that call to printf so that you see call printf in IDA versus call to some address, and then it's up to you to figure out what that call is. Everything is going to be saved in a database. So once IDA has parsed that executable, everything is saved in a database, and it no longer needs that executable. When you modify anything in IDA, you're actually modifying the database, and you're not touching that executable again. It's not executing it, it's just loading it into this database. So every time you load it, once it's initially been parsed, you're just loading that database. Okay, and now it advances to the next instruction, and it repeats. It just continues to repeat that process over and over. There are 2 disassembly methods, and it's generally just good to understand which methods are being used based off of what tools you're using. You can see here at the very bottom of the slide that for this linear sweep method that we're about to talk about, GDB, WinDebug, and the object dump utility use those. Hopefully you use GDB in 314, or at least got to see it a little bit. We'll be using predominantly WinDebug through this course. A little bit different. and then the other method, which is recursive sweep. And we'll talk about that here in a moment. So what is linear sweep? Well, it starts at the beginning, wherever that initial entry point was identified, and it just begins to disassemble instructions. It's easier with fixed width because the disassembler has less work to do, and that it just simply needs to read those whatever size, whatever number of bytes as an instruction. With the variable width, then it has a little bit more work, and that it has to determine what is the exact size of that each instruction. The pros here, it's fast, depending on the size, of course. The cons is that we can have data located within the actual instructions, and what this can do is it can corrupt the process, because now as that disassembler is going through, it's mixing up instructions with data, and it's treating data as an instruction. And so if you have a few bytes of data that now get interpreted as instructions, that can throw off the the resulting and the rest of the disassembly from there. So it can be a problem. It's not critical that we understand this, because in this course I'm not going to throw any like weird problems in the programs that disassembles funny. If you happen to run across something, if IDA happens to not do something correctly, then that just was an accident, or it was a failing on IDA's part, or something. So don't have to get too worried about that. Just know generally that it exists, and these are the primary differences between the two methods. It also ignores branch context, because it's just doing instruction after instruction after instruction, right? It's just looking at them sequentially, linearly, and disassembling those for you. Here's an example right out of our IDA Pro book showing that problem right that we just previously talked about, is that sometimes as it's doing that linear sweep, it can make a mistake. And what you want to be looking at here is this instruction 1-2. You can see we have this jump to D word pointer edx times 4 plus, and then this address right here, 401257. So what it's saying is that the next instruction, E012, is loop NE 40126B. And what we're generally looking at in this listing, and again, we'll get into this in more detail as we start studying the IDA Pro interface, we have addresses, we have opcodes, and then we have the resulting instructions. These opcodes, that's the binary, right? And you'll get to know some of these probably by the end of the course if you don't know some already. But this is primarily what we're looking at here. The next instruction, though, it disassembled as E012. The problem is that that's not correct, right? 401257, if you read in the book, it says that's the beginning of a jump table. So 401257 is our jump table. The addresses for a jump table, so that means that it's just a series of addresses. And what they actually are, and you have to remember endianness here, the addresses would be 004012E0, and then 00401228B, and then 00401290, 00401295. Right? We can see that these are the addresses right there. And because the disassembly messed up right here, it also screwed up all the rest of this. Everything else is not correct now. And so you could fix it. One of the powerful features with IDA Pro is that you could come in here and you could fix this. You could say, no, you disassembled it wrong. This is actually supposed to be an address because it's data. It's not an instruction. Right, but we won't have to do. I'm not planning on doing any of this. So if this does happen to you, it was an accident. So let me know. I'm certainly curious to see what happened, but I don't expect it to. It hasn't happened in the previous semester. Okay, recursive descent starts at the beginning, and it uses control flow to decide where to descend to, where to go, and it also will keep a list of addresses where to explore. So this gives you essentially generally a better disassembly, in that it's only going to go to memory locations and disassemble those instructions if it's referenced. So you have different types: sequential, conditional, unconditional, and we'll talk about those throughout the course. Sequential just means one instruction after another. If you had an add or a move, it executes that instruction and it goes to the next. You have conditional, so jump if not 0, jump if 0, right? Jumped on a condition, so generally going to check the flags register. You have an unconditional, like a jump or a call, and that you're going to go to that address regardless. And so as it's being disassembled, it's taking instructions like that into account, and going to those addresses, going to those locations in order to disassemble if they're being referenced. It's more accurate. It is faster. The cons is that not all code may be disassembled, because as the program is being disassembled statically, it just may not be called, it may not be used, or the location may be dependent on a value that is generated dynamically during runtime. And so at the time that it's being disassembled, it's not available. The address is just simply not referenced. So there are some limitations. We can also run into some packers, and we most likely won't talk about any of these throughout the course. Packers and obfuscations. So if the code is actually packed or obfuscated, then we'd have to go through the process of deobfuscating or depacking it in order to get the actual code. You have dynamic code. You can have some that can download code or download instructions on the fly and execute it. So maybe you're looking at a program and all the code's not even there. You can also have misbehaving functions, some that modify the stack or generally alter the way in which the program is going to behave. And that can cause problems in the analysis, whether it's static or dynamic, and trying to understand how that program works. Okay, that's it. So that was an introduction here. And again, just big picture stuff. So we'll get much further into the details of what's important for the course here as we begin to get into the labs. So just a big picture overview. Let me know if you have any questions. Otherwise, I will talk to you guys in the next video. Thanks.